In this lecture, I'll talk about partial derivatives and the gradient vector. The change in the function along the lines formed by the variables, let's say the x, y, and z axes, the change along those lines is called your partial derivative. It's denoted as shown down here. So instead of writing df by dx, which implies the total derivative, we write instead this Greek delta df by dx, and that means the partial derivative. So this is the total, and this is the partial. To save space, you can also write f with a subscript x to mean the partial with respect to x. These partials are really the limit of difference quotients, just as the total derivatives were for functions of a single variable. It looks a little easier when you see an example, but basically what we're going to do is take the partial with respect to one variable, in this case say x. To do that, we hold all the other variables constant. But then when you go to evaluate the derivative, you must supply values for all variables. So here's an example. Let's take the partials of the function y squared sine x. This is a function of two variables. So we can take the partial with respect to x. We can also take the partial with respect to the other variable y. So here's the partial with respect to x. We assume that the y squared is a constant and just take the derivative of sine x and get cosine x. Now we can take the partial derivative with respect to y by holding the x constant. So sine x is assumed to be a constant in this case, and all you take is the derivative with respect to y, which is 2y. Now if you want to evaluate the derivative at some point xy, you have to supply both values, which would be, for example, at the point 0, 2, you're evaluating at 0, 2, we get 2 squared times cosine of 0, which is 4. That's for the partial with respect to x. The partial with respect to y turns out to be 0. And this sketch shows the significance of these partials. Here is a function of two variables. This is f of xy. It's shown in that green. Right. At this point right here, we have the partial with respect to x. This is f of x. That would be the derivative in the direction of x, so parallel to the x-axis. And now looking the other way, you have the partial with respect to y. And it is, if you drew a tangent line through that derivative, use that derivative to create a tangent line, that line is parallel to the y-axis. Well, its projection is parallel to the y-axis. And it's very common to take these partial derivatives and organize them into a vector called the gradient vector. And there's some results from the gradient vector that I will show in the lecture on directional derivatives. But basically, the gradient vector is used to calculate the direction in calculate the derivative in any direction, not just parallel to the x or parallel to the y-axis. And also you can use these partial derivatives and this gradient vector to create a linear approximation to the surface. So here's the gradient vector. To construct the gradient vector, you take the partial derivatives and then organize them, putting the partial with respect to x in the y direction and the partial with respect to y in the j direction. If f is a function of three variables, then you'll have the partial with respect to x in the I direction, partial with respect to y in the j direction, and then you would have also the partial with respect to z in the k direction. This is a vector, and it is denoted by this upside down triangle. Sometimes called nabla, but this is that's the gradient. That means gradient vector. Sometimes it's written out like that. So for the function we were just talking about, y squared sine x. It has a partial with respect to x of y squared cosine x, a partial with respect to y of 2y sine x. The gradient vector is y squared cosine x in the I direction plus 2y sine x in the j direction. So in homework there was this function, e to the x plus x times natural log of 1 plus x plus y times the natural log of x plus, y plus 1 and x plus 1. So you want to find the gradient for that. First you find the partial with respect to x. So I hold y constant, and e to the x, of course, is just e to the x. Take that derivative. In the next term, we have x times the natural log of y plus 1. But that whole thing is a constant, so taking the derivative of x times the natural log of y plus 1 results in only natural log of y plus 1. It's a constant. And then for the third term, have y over x plus 1. Using the derivative of log, and then the chain rule, of course, gives only 1. So here is the partial with respect to x. Then you do the same thing with respect to y. So I'm taking the partial with respect to y, which is the same as f with a y subscript. So the first term, of course, has no contribution. The second, we have x over y plus 1. And from the third term, we have natural log of x plus 1. So for the gradient, you just put all that together. So the gradient would just be e to the x plus the natural log of y plus 1 plus y over x plus 1, and that's I, plus whatever that is, x over y plus 1, I'm running out of room, plus the natural log of x plus 1, and that's in the j direction. So I've created this vector. Gradient of f, that's a vector. The gradient has the usual laws, or the usual rules for derivatives. You can pretend this is as a derivative. So if you take the gradient of alpha x f plus beta g, you can just pull that gradient through. Get alpha gradient of f plus beta grad g. Of course, that's a linearity rule. Remember, instead of trying to have one rule for f plus g, another rule for f minus g, and a third rule for alpha f, it's more common to combine all those into alpha f plus beta g and apply the rule there. This is this linear combination of f and g. That's what this is called. Also, the product rule holds just as it does for derivatives. The gradient, of course, is not a unit vector necessarily. It will have a magnitude and a direction, just like any vector. So its magnitude, let's look at it again. Okay, whoops. The gradient of f is fx in the I direction plus fy in the j direction. So obviously you can see what the angle is. Angle is the arctangent of fy over fx. And then the magnitude, say squared, you can take the square root later, is a dot product with itself, and that's where you get fx, the derivative with respect to f squared plus the partial with respect to y squared. There's some very important results concerning the gradient. The function, that means the underlying function f, is changing most rapidly in the direction of the gradient and also in the direction opposed, in the direction 180 degrees from the gradient. Is increasing most rapidly in the direction of the gradient. It is decreasing most rapidly in the direction 180 degrees from the gradient. And the function is constant in the direction perpendicular to the gradient. That means the gradient is perpendicular to those level surfaces, or what you would call those contour surfaces, or the traces in z of the function itself. And that will be shown and discussed more in the next lecture.